All right, then we are going to introduce our next speaker. It's Wenzhen Yuan. She is an assistant professor in the Robotics Institute, Carnegie Mellon University, and the principal investigator of the CMU RoboTouch Lab. She received a master and PhD degree in mechanical engineering from MIT and bachelor's degree in mechanical engineering from Tsinghua University. She also worked as a postdoc researcher at Stanford University. Her research interest is in robotic touch sensing and robotic perception in general. And I don't think we can hear you. We can see the slide.
Okay, finally it works, right?
Okay, perfect. Yeah, now it works.
Thanks very much for the introduction. It's really a big pleasure to have a chance to come here and introduce my work of using high-resolution tactile sensing for perceiving deformable objects. So today I'm going to talk about more on the perception side, especially what happens if a robot can use tactile sensing to perceive those deformable objects. And particularly, I will consider two cases of deformable objects. So one of the examples of the deformable objects are things like avocado. So this kind of objects are made of softer materials. So we can perceive like some of the avocado is softer than the other ones, or we may say that deformable. It's just because like the material made of those objects are deformable and have different level of hardness. And the other kind of deformable objects are things like fabrics and of course ropes, as we just heard from Dimitri's talk. So those kind of objects, if we consider the material itself, it's not that much pressable. So like if you have a very thin layer of fabrics and you want to press on it, so it usually doesn't deform a lot. But if you consider the global structure of those objects, there's lots of they may have deforms a lot, but it mostly comes from the on the structure side. So as humans, it's very natural for us to perceive those objects or touch. For example, as soon as we are touching a avocado, so we can quickly learn whether it's a soft avocado or it's a hard one. And when we touch a piece of fabrics, we can quickly learn like how soft it is, how deformable it is, how stretchable it is, etc. So we have a good use of our touch sensing. So, but the things I've been trying to figure out with my colleague is that whether a robot can do similar kind of perception with tactile sensing. So when we talk about tactile sensing for robots, this is a very typical scenarios we may think of. So here a robot is trying to grasp an egg. So we know that the robot wants to use a moderate force for the grasping, so that it's not really crushing the eggs. So here the robot has equipped it with two tactile sensors on the two fingertips. And those tactile sensors are able to detect the distribution of normal force during this operation. So that like the good thing is that like the robots can detect like where is the contact, what's the approximate shape of the contact, and what's the force of contact. So that is very helpful in this like specific egg grasping task, because the robot want to control the force of contact to prevent crushing the objects. So that like by measuring this normal force on the fingertips, the robot can understand, oh, hey, this is a acceptable force, it's good, so we can grasp the egg. So, but we can also see that for this kind of tactile sensors, so although it's very helpful to get some good estimation about the contact areas, the geometries, the contact force, but it's still pretty limited. So the information you can get is very limited, especially if we consider like some more subtle properties of objects. It's not really enough to do the job. So here we propose another potential solutions to this challenge by introducing a type of high-resolution tactile sensor called GelSide. So this is invented by my PhD advisor, Ted Edelson at MIT. So the basic idea is that we use a vision-based method to detect touch. So in other words, we embed the cameras into this structures, and on the top on the surface of sensors, we use a piece of deformable elastomer as a medium of touch. And we also designed some optical structures to make sure the deformation of this soft surface can be inferred from some optical signal that can be observed by the camera. So in this way, we are able to get a very high resolution details of the objects being touched. So especially regarding to its geometry, but we can also get some information about the force and torque on the contact surface. So here shows an example of how the sensor works. So the first window here is a human holding the sensor, touching different objects on different locations. So the middle image here shows the raw output we get from the GelSide, the camera into the GelSide, or in other words, it's also the output we get from the sensor. So there are two things happening. So on one hand, we can see the background colors from this image. Like normally it's like almost a gray colors, but upon contact, there could be some change of the colors. And that change of the color is highly relevant to the geometry of the objects being in contact. And since we have like all those fine details on the this soft surface, and we use a camera to detect all the details, they're able to see the very fine details of the geometries from this change of the color. So on the other hand, we can see all those black dots. So they are physically painted on the surface of this sensor. So that and we can also track the motion of the dots. And they are very informative of the contact force and torque, especially the shear force and in-plane torque. So I'm actually drawing the tracking the motion of those markers in the third window here as those yellow arrows. And the direction of the motion of those arrows and the magnitude of the arrows are very informative about like whether it's a normal force or shear force and what's the magnitude of the force. Okay, so there are some questions, some chat windows. Let me see whether I can. Okay.
I think it's unrelated to the talk. It's for the next session. Sorry.
Okay.
We will have the questions at the end of your talk.
Okay.
Thanks.
So here we have the sensors, and so we also attach that on a robot, so on a robot gripper, so that the sensors can work as one of the fingers of the robot, and the robot can carry the sensor to detect different objects and perceive those important tactile informations upon contact. So when I look at those videos like about the contact sequence, so we can see lots of interesting things happening. So of course we can see those change of the geometry and the force, but also like I said, it is a change because the sensor itself is soft. So the contact is not like at one moment, but it's a dynamic process. And the good thing is that we can use our sensors to detect all the information happens in this dynamic process, like how the contact geometry changes, how the contact force changes. So this is pretty similar to the process of human touch. So we know that as humans, the fingertip is most important things for us to perceiving the environment, the external objects. So because like at least on the first step is that on the skin of our fingertips, there are a bunch of mechanical receptors to help us to understand what's the force information on the skin side. But if we take a look at like the structure of the fingertips, it's actually a soft fingertip, and it's wrapped around the rigid bones. And upon the contact, there's lots of deformation on the soft fingertip itself. And that is a very important type of physical interaction between your fingers and those external objects. And when we see that we have those mechanical receptors on the fingertips, we can detect the contact, we can detect the informations. So we know where is the contact, we know the force, but also it detects this dynamic process of the contact. It helps to understand like how your finger, how this soft fingertip is deformed and how that reflects about like the important information about this external environment. So if we consider a basic problems about like perception of deformable objects, so that could be estimate hardness of objects. So a typical way of asking a robot to do this is building a structure like this. So we can ask a robot to use an indenter to indent objects with well-controlled speed, so that we can measure the force during the process, and we pair that with the motion, the constant speed. Since the force is known, the trajectory is known, the speed is known. So we can just use the basic relationship between like the contact force and the indenting depth to indicate the hardness of the objects. But this method is very constrained, since that it requires very precise control of the motion and very precise changing the sensing. And it only works with objects that has a flat surface or has a very well-constrained categories of the geometry. But on the other hand, there are also some studies about how humans do this kind of things. So as we talk about like in the previous slides, human has these soft finger structures, and we learn lots of information from this dynamic interaction between the soft surface and the external objects. So actually, there has been a human study showing that if a human perceiving objects in a passive ways, or in other words, is as shown in these videos, the human is now moving, but an external object is touching the fingertips of this human. So that in other words, like this human has no control of the displacement. They have no clues about how hard was the displacement of this pressing or indenting into the objects, but they could still have a very good perception of what's the hardness of these objects. So this indicates that, like, in many cases, humans has more reliance of this dynamic process that can be perceived from the skin about the deformation of these soft fingertips. So the question is that, can we use the lessons from the humans to get some better perceptions of the objects as well? So we did a simple experiment with our GelSide sensor, which has a soft surface and can perceive the geometry of the contact objects with very high resolution. So we handheld this GelSide sensors and press on objects that has a hemispherical shape, and it's also actually deformable. So of course, like the most important thing we can get from the GelSide sensor is the geometry of the objects. So that is because the sensor's soft surface deforms during the process. But also, the objects may also deform if the object is soft. And we found that the softer the objects are, the more the objects may deforms during the pressing process. And of course, usually the normal force is smaller during this process. So the good thing is that we can perceive the geometries exactly. So here is the sequence of the output we can get from the GelSide sensor in these pressings. So we can see that from the window here, so there is a round area, it's growing larger and larger, it has a distinct color from the backgrounds. That indicates the geometry of the object surface. So since this is a hemispherical surface, so the contact area is a dome shape, it's round and expanding as the force grows larger and larger. So on the other hand, we can also ask the sensor to press on an object that is of exactly the same geometries, but with a much softer, So we can perceive some information like this. So it's still a round contact areas. It still has a dome geometries, but we can see that the color here is much shallower. So that is because the surface is much flatter in this case. Why this happens? Because the object is much softer and has much more deformation. So that means like during the press, it's more likely you will flatten out the objects. So the good thing is that we can perceive those like very fine, very small change of the object geometry with the GelSide sensor exactly. And we can use that as a clue to help us to estimate how hard is this object. So of course, another thing we can consider is the normal force. So as our intuition tells us, like when we press on a softer objects, the force is generally smaller. So on the other hand, in the other words, that means like if we consider the motion of the markers, which indicates the pressing, the contact force, so we will see that like when we pressing on harder objects, the marker will have a significantly larger movements. So that means that represents a much larger normal force. And but if we are using our sensor to contact a softer objects, as shown in the second row here, the motion of the markers, as the yellow arrow shows here, is much smaller than the first case. So that means like the contact force is much smaller. So that there are two most important clues here. So one is the contact force, one is the geometry that can be indicated from the colors. So we can just we just train the simple regression models to measure this dynamic change of those the colors, as well as the motion of the markers through the process. And we use that to estimate the hardness of the objects through this from this contact sequence. And it works pretty well. So, but also the constraint is that it only works for the objects with a spherical geometry, so where we know exactly what's the what we can predict as the contact geometry changes, and then we can simply build our regression model based on the colors and based on the motion of the markers. And so that means like at least by theory, this clue works well for helping robots to estimate hardness, and also for understanding those spherical objects. But it may turn out to be very challenging if we consider the contact the detection of an arbitrary objects, which may have very unpredictable or unknown geometry. So we know the physical foundation is still there. Like during the context, we can consider the change of the geometry, the change of the contact force. They're still highly relevant to the hardness level of the object itself. But the big challenge here is how can we build a model to describe these changes, to describe these differences across material objects with different hardness. So then we turn to data-driven models to solve the problems with neural network method. So that means like we build a big data set of using a tactile sensor to contact objects with different hardness, different geometries, and hope the neural network can learn something. So firstly, we build this object data set. So we use silicon to cast based on like using different kind of modes, including some of the simple shapes or more complicated shapes. So we use different type of silicons so that we can control the hardness of the samples. And we also consider some of the natural objects, such as the fruits, candies, or human bodies, or some toys. And we don't have a good understanding about like the ground truth hardness level of those natural objects, but they can be a good test objects to give us some intuition about like how our method works to generalize on the objects that we really don't have any background knowledge about how hard they are. So then we collect a data set with a GelSide sensor, either as a human to conduct the contacts, or we make a robot to conduct the contacts. And so we use both ways to contact those objects, the objects in our data set at different locations, different force, different trajectories to make sure we have enough varieties in our data set. And then we train a neural network with a structure like this. So the input of the neural network is a sequence of the contact of the GelSide images. So that means like we can see what happens on a single contact case, and we can also see how this contact information changes as time proceeds. So that there are actually, and then we build this network with a combination of a CNN structure and RN structures. So the CNN structure is more important to tell about like spatial information. In other words, it tells about like in this single moment, what is the geometry of this contact surface and what's the contact force. And the RN structure is more important to tell about temporal information. It's about like how this geometry changes as time goes and how the force changes as the time goes. And finally, we make an output about the single numbers regarding to the hardness level of this objects being contact. So to test out our data set with lots of silicon samples where we know we have good understanding of the ground truth, we figure out like with the case working on like objects that has a same shape on the hardness, or like totally new shapes, or if the contact mode is different, like if we train on human data and test on like robot data, our network can do a reasonable job of estimating the hardness levels of those objects. And of course, we also have lots of interest at the first question about whether we can estimate the hardness of avocado. So here we use 2 avocados and ask a human to rank them from soft to hard. And then we make a human to press GelSide sensor on the surface to guess the sequence of the data and estimate the hardness of avocado from the data. And we found out that the estimation from the GelSide from the neural network matches the estimation of humans. Okay, that's a part of hardness estimation for the objects that is made of soft materials. So the second part I would like to talk about like the perception of fabrics, which is a good representation of the objects that is structurally deformable. So of course, like as a humans, we can get a good understanding of the fabric properties through touch, but like what can we do with the tactile sensing? So here we consider the case of natural clothing. So here we ask a robot with a GelSide sensor to go to touch different type of clothes in their natural states and take a look at what kind of data we can get through the process. So here the third one shows the like the tactile data we can be obtained from the GelSide sensor through the entire process when contacting different types of the clothing. So we can see that there are multiple things happening. So on one side, so it's like we are able to detect very fine details about the contact surface. So we can see the geometry of the textiles very clearly. Like for example, this leather has this very dull structure, dull texture, and this is this clothes with polyester shells will have another type of the texture. But on the other hand, if we can also get lots of information from the overall change of the contact area. Like, is it like a very, is the contact area very large, covering the entire surface, or is much more smaller and only covers a smaller surface? And also there are some foldings happening during the context, like what kind of information can we get from those foldings? So all those information is very informative about like what's the material type of the object of this material it is, like how deformable it is, and what does it mean for a robot or for a human to understand this type of material. So then the question is that like, how can we understand them? So we actually collect a big data set of like 150 clothes with a wide variety regarding to the materials and type of the clothes. And we ask the robot to explore them and touch on different locations and collect a very varied data set like this. So as we said, as we just go through the process, we can see lots of difference in the textures, but the overall shape and structure of the clothing in context. And we want to have a good understanding about what we can learn from those tactile data. So again, we train a convolutional neural network to learn those relevant properties from those tactile images. So regarding to the properties or the ways we describe the clothes, so that's actually a big challenge. It's like, how can a robot understand those clothings? How can the robots use the understanding to help it to better manipulate or interact with those clothing in the daily life? So we use a reference of human perception. Like we ask human, what do you think is the most important things when you consider the properties of the clothes? So we summarize 8 physical properties to describe the clothes, like thickness, smoothness, fuzziness. And we also consider some semantic properties, like what's the wearing season of those clothes and how you should wash those clothes. So hopefully the robots can use those semantic properties to get a better like sorting or arranging of those clothes based on those understanding. And for the ground truth, we ask a human to do the labeling. Like we ask human to put put all those properties into several levels and label different clothes as different levels. And we use that as a ground truth label. And hopefully the robots could come up with a prediction that is similar to the perception of human. So that like finally we turn this into a classification problems, but it's like multi-classes classification. So we use a neural network as and take the tactile information from GelSide as the input and make a classifications based on like different properties and according to different levels, discrete levels in these properties. So we figure out like with these basic structures, we can do a pretty decent work job on the object clothing that especially can be seen included in the training set. So for example, if we take a look at thickness, the chance of getting it correct with a random guess is 0.2. That means we are actually making 5 degrees regarding to the thickness level of a piece of cloth. So if we ask a robot to explore a cloth that is included in already seen in the training set, but it's totally new touch, so we can get the prediction correct with a chance of 89%. But of course, if we are exploring some unseen cloth, the performance is compromised. But it's still like much higher than the chance. So the next challenge we want to make is that we want to make the robots to explore the clothes on its own automatically. So we design a system like this. We want to have the robots with a gripper and tactile sensors on their fingers, but also use a cameras, which is actually a Kinect here, high up here, which is really helpful to detect the global information. And the global information will guide the robots to understand where to touch, so that the robot will choose a point and go ahead and just use the finger to squeeze on the piece on this part of the cloth and get a sequence of tactile data. So, so other than of course, there are also on the robotic side, we want to understand how can we figure out the place to touch from the visual information. So we figure out like a hack into this problem is that there are lots of foldings on the clothing, which can be represented as the edges from the depth images. And those are mostly the places very easy for the robot to generate some good tactile signals. But of course, like some of those edges are good, what we call good edge points, and some of them are bad. The bad edge points where like we can hardly get a good tactile image from them. So we train another neural network to figure that out. So finally, we have like two neural network structures. Firstly, we use a depth neural network to figure out whether a candidate grasping point is a good touch point or not a good touch point. Once we figure that out, we ask the robot to go ahead to collect some tactile data and feed that into the second neural network and use that to get a bunch of perceptions of the properties related to this clothing material. But then there's a question like, what happens if something goes wrong in the middle? What happens if it's not really a good point to touch and the data the robot get is not good and the robot can hardly predict the hardness, the properties of this piece of clothing? So the easy answer is that the robot can just go back and redo this exploration procedures. So we actually design this retrial loops by estimating how confident the robot is when predicting the properties of those clothes. So if the confidence is not very high, or in other words, like the classifications vectors is not very concentrated on the only one class. So when we come to the conclusion that it's more likely this is not a good tactile data, and the robot will just go ahead and touch the cloth again, collect another piece of data, tactile data, and use that to estimate the hardness, the property level again. So here shows an example of how this process works. So here the robot firstly tries to touch somewhere. It's actually a good place, but unfortunately there is actually a button buried in the cloth. So that turns out to be very confusing. So the robot decides, okay, I'm not very confident here, so I will lay the cloth and do a touch again. So this time is a backlit place. So we can see that there's nothing in contact. The robot will figure that out immediately because there's no clothing in the touch information. So then it generates a third touch. So this time is very nice data. The robot is very confident about its predictions. So here is the robot is actually trying to do something further to decide how to wash this cloth and put the cloth into corresponding washing bin. So with this mechanism of retouch, the closed loop explorations, we perceive a much better performance regarding to the property estimation. So these are the results from working on the object clothing that is not included in the training set. So for example, on the thickness, if we are asked the robot to only touch the cloth once, we can get things correct with a chance of 0.59. But if we ask the robot to do a closed loop explorations, we can get things correct with a chance of 0.65. Okay, so that's the end of my talks. So as summaries, we try to use data-driven method to understand the properties of deformable objects with tactile sensors. Especially, we consider two types of material objects. One is like objects has softer materials, and we try to estimate hardness from the deformations and contact force change. And we also consider objects that are structurally deformable, like fabrics and clothings. And we try to estimate a set of physical properties from the tactile data. So at the last, I would like to thank all my colleagues working on those projects, and thank you for listening.
Thank you very much for the very nice talk. We have one question from the audience, and it's asking if this test object, I think it was the silicon ones, are available for viewing or files for download. If someone could kind of recreate this.
We have all the data online, open source. We can, I think the easiest way is search my name online, so there you can have access to all those data sets from my personal website. But also it's a big challenge about the physical data set. Like we actually spend lots of time collecting this data set of silicon samples and the data set of clothing. So some of them are still available in the lab. So if you're in US or can come to my lab, so we can talk about exploring those physical data set or mail them to you. But generally, they are not that easy to access as a digital data set.
Okay, thanks. And then I have a question of my own. Like when you explore these softness measures, like there are these traditional hardness measurements, right? Like the Rockwell or the Moore hardness scale. Like, are you planning of kind of extending those towards more the softness? Because if I remember correctly, all this material would fall in the softest category of all of these hardness scales, because they are really for minerals or rigid objects, not really deformable.
So the ground truth we use actually is the shore hardness, and we use the softest. The softest measurement of shore hardness is shore hardness 00. So we can measure the hardness of objects ranging from like very, very soft elastomers to the objects with the hardness similar to the rubber. So we figure out like for humans, those are the range of the objects, like the hardness perception is most important. Of course, there are also like engineering level of hardness, like comparing the hardness of wood materials, steel materials, or some other metal materials. I don't think like it's very important for human as a part of perception. So we are mostly focused on the range like a human is perceivable.
Thank you very much. We have another question from Alberta Longini. Have you considered also sliding exploration actions, like not just pressing, but sliding?
So yeah, that's a great question. So of course, there are different ways we can ask a robot to explore the material, different objects. So sliding, pressing is one thing, like it's mostly informative to tell about hardness of the objects. But of course, like sliding is helpful, especially if we want to estimate the friction of the objects. So we do have lots of interest on that. It's not, we don't have any results in that direction yet, but it's definitely a good way of thinking about how can a robot explore the objects.
Thank you. And we have one more question from the Slido. Are the sensors going to be commercially available?
So my PhD advisor Ted Edelson co-founded a startup of GelSide on this GelSide technologies. So based on my recent touch with them, they have plans to commercialize one version of the robot sensors and might be on market probably very soon. So I encourage you to keep an eye on their company. So hopefully they will make the life of researchers much easier to access this kind of signals.
All right. Thank you very much again for a very nice talk. And then we are going to move on to the next scheduled event.